This research introduces a novel framework called Logic Distillation, LD, to enhance the planning and decision-making capabilities of smaller language models, S-LLMs, by leveraging the powerful logical reasoning abilities of larger language models, L-LLMs. The authors acknowledge that while L-LLMs, such as GPT 3.5 and GLM-4, demonstrate superior performance in tasks requiring logical reasoning, their computational requirements make them impractical for deployment on most devices. On the other hand, S-LLMs, like GLM-49B and Llama 7B, are more accessible due to their compatibility with consumer-grade GPUs and cost-free nature. The paper highlights the limitations of traditional knowledge distillation, KD, methods, where S-LLMs merely mimic the outputs of L-LLMs without acquiring their powerful logical reasoning capabilities. To address this challenge, the proposed LD framework employs L-LLMs to break down complex instructions into discrete functions and illustrate their usage to establish a function base. Subsequently, LD fine-tunes S-LLMs to learn the logic employed by L-LLMs in planning and decision-making tasks. During testing, a retriever identifies the top K relevant functions based on instructions and current states, which are then selected and invoked by S-LLMs. Finally, S-LLMs produce planning and decision-making outcomes, function by function. The authors demonstrate that with the assistance of LD, S-LLMs can achieve outstanding results in planning and decision-making tasks, comparable to, or even surpassing, those of L-LLMs. This is exemplified through experiments involving a pursuit game, where blue dots controlled by different L-LMs aim to capture orange dots governed by GLM-4. The results show that after applying LD, S-LLMs significantly improved their performance in the game, illustrating the effectiveness of the proposed framework. In conclusion, the paper presents a novel approach to empower S-LLMs with the powerful logical reasoning capabilities of L-LLMs, enhancing their performance in planning and decision-making tasks. The proposed LD framework offers a promising solution to bridge the gap between the capabilities of L-LLMs and S-LLMs, paving the way for more efficient and accessible AI models. The pursuit game scenario exemplifies the limitations of small language models, S-LLMs, in planning and decision-making tasks when using knowledge distillation, KD, from large language models, L-LLMs. In Figure 1, 4 dots are initially positioned, demonstrating the effective planning and decision-making of the L-LLM, GLM-4, in understanding game rules, as shown in Figure 1b. However, the S-LLM, GLM-49B, lacks proficiency in following rules, as seen in Figure 1c, and the issue with KD is evident in Figure 1d, where the student model merely mimics the output of the teacher model without comprehending the logic behind it. The limitations of S-LLMs with KD are summarized as 1. Ineffectiveness in following complex instructions, and 2. Failure to comprehend the logic of L-LLMs. Inspired by the work on translating natural language to code, the authors propose logic distillation, LD, to break down the planning and decision-making logic of L-LLMs into multiple stages, represented by specific code functions. S-LLMs then engage in planning and decision-making by learning and applying the pertinent functions. LD involves leveraging the comprehension and logical reasoning capabilities of L-LLMs to decompose the rules governing planning and decision-making tasks into multiple stages, forming different functions. These functions, along with their comments and usage examples, are integrated into a function base, which is used to fine-tune S-LLMs to enhance their ability to invoke relevant functions. The authors also propose transforming generation into selection, where LD employs a retriever to provide top relevant functions based on the current state and instructions, enabling S-LLMs to select and execute functions from this set. Figure 2 illustrates the difference between KD and LD, where KD emphasizes the imparting of content, while LD concentrates on the underlying logic of task execution. The main contributions of this paper include analyzing the issues of knowledge distillation in planning and decision-making, proposing logic distillation to enable S-LLMs to accomplish complex tasks, and conducting experiments to validate the effectiveness of the proposed method. The paper also reviews related work on large language models, their applications, and their limitations due to size constraints, which led to the development of smaller LLMs. Logic distillation, LD, is a methodology that enables smaller language models, S-LLMs, to acquire the planning and decision-making capabilities of larger language models, L-LLMs. The LD framework consists of three components: L-LLMs, a retriever, and S-LLMs. L-LLMs decompose human-provided rules into basic functions, creating a function base that includes these functions along with their user manuals. The retriever retrieves the top K functions relevant to the current stage and input, while S-LLMs select the appropriate functions to plan and make decisions. In interactive planning and decision-making tasks, LD leverages L-LLMs to instantiate the reasoning logic through functions, using the probability distribution of generating a current token based on a context of previous tokens. This approach enables the creation of a function base, which includes functions and user manuals. The retriever is designed to handle function bases of different scales, proposing two solutions tailored for this purpose. Notably, while S-LLMs are more flexible than L-LLMs, their performance is significantly inferior. To address this, knowledge distillation, KD, of LLMs has become a focal point of related research, where LLMs serve as teachers and S-LLMs as students that learn to mimic the outputs of teachers. Other works have focused on the reasoning steps of LLMs, such as extracting rationales as additional supervision for training S-LLMs within a multitask framework or incorporating system messages to facilitate student models' comprehension of the reasoning process. The Logic Distillation (LD) framework is a novel approach designed to enhance the capabilities of small language models, S-LLMs, in following complex instructions and performing multi-step reasoning tasks. This is achieved by transforming the function of S-LLMs from generation to selection, allowing them to choose appropriate functions from a provided set for various stages of problem solving. In the LD framework, large language models, L-LLMs, are used to generate functions and their corresponding user manuals, which are then stored in a function base. S-LLMs select the most suitable function for each stage of the task, based on the input X and the top K functions retrieved by the retriever. The selected function is executed to obtain intermediate results, and this process continues until the task requirements are met or an emergency situation arises. Emergency handling in LD involves S-LLMs generating emergency functions and adding them to the function candidate list. This enables S-LLMs to respond to unforeseen circumstances, such as navigating through archipelagos or avoiding whirlpools when controlling unmanned vessels. Theoretical analysis demonstrates that selection is better than generation due to its lower entropy, as shown in equations 7 and 8. The Lagrange multiplier method is applied to obtain the optimal probability distribution for each token in the token list, enhancing the efficiency and accuracy of the selection process. The proposed LD framework has several advantages over traditional knowledge distillation, KD, methods, including preserving more general capabilities of LLMs and requiring S-LLMs to remember only the usage rules of functions rather than memorizing massive LLMs outputs. This approach is summarized in Algorithm 1, which outlines the testing of logic distillation and provides a systematic guide for applying this framework in various applications. In pursuit games, large language models, LLMs, can enhance the planning and decision-making capabilities of smaller language models, S-LLMs, by decomposing complex tasks into simpler subtasks. The authors introduce language decomposition, LD, a novel method that initializes a function base with the LLM, where the LLM decomposes rules and instantiates planning and decision-making logic into multiple functions. This allows the S-LLM to accurately invoke relevant functions and complete the planning and decision-making process. In the context of the pursuit game, two sides are involved. One LLM manages 3 blue dots, and another controls an orange dot. The objective is for the blue dots to capture the orange dot within a certain distance. The authors compare their approach with baselines like knowledge distillation, KD, and demonstrate that LD outperforms these methods in maintaining stable outputs for S-LLMs. The paper presents mathematical equations to calculate the maximum value of H generation and selection, which represent the entropy of generation and selection, respectively. The maximum value of selection is significantly smaller than that of H generation, indicating that selection is more effective in maintaining stable outputs for S-LLMs. Experiments involve initializing 221 sets of starting positions randomly and generating 103,355 sets of outputs with the LLM for knowledge distillation. The S-LLM is fine-tuned with LoRa based on these outputs. For the LD approach, a function base is established with the LLM, and experiments verify its effectiveness in enhancing the planning and decision-making capabilities of the S-LLM. Overall, the paper presents a novel approach to enhance the planning and decision-making capabilities of S-LLMs using language decomposition, demonstrated to be effective in a pursuit game scenario and outperforming baselines such as knowledge distillation. A comparative analysis of large language models, LLMs, in a pursuit game, where the objective is to capture an orange dot with blue dots, reveals distinct performance differences. Table 1 illustrates that the S-LLM model consistently fails due to rule violations, while L-LLM exhibits superior comprehension and adherence to instructions. The S-LLM's performance improves when utilizing knowledge distillation, KD, or learning to demonstrate, LD, with LD demonstrating the most significant enhancements. In terms of local planning and decision-making, figures 5a through 5d show that S-LLM with LD outperforms other models by effectively grasping the logic of L-LLM, leading to successful game outcomes with fewer steps. This is further supported by the global comparison in Figure 6, where S-LLM with LD demonstrates more direct and efficient strategies for capturing the target, requiring fewer steps compared to L-LLM. The findings suggest that LD is an effective method for enhancing the S-LLM's planning and decision-making capabilities, allowing it to better understand and execute complex instructions. The results also underscore the importance of understanding the underlying logic and rules of a game, as well as the ability to adapt and make decisions based on changing circumstances. The pursuit game with emergencies is a novel scenario introduced in the research paper, where a 5x5 restricted area within the game plane assesses the capacity of different large language models, LLMs, to handle emergencies. Table 2 illustrates that L-LLM achieves a success rate of 90% in this scenario, while S-LLM with knowledge distillation, KD, achieves a success rate of 52%, with failures resulting from rule violations. In contrast, S-LLM with logic distillation, LD, surpasses L-LLM's success rate by 10%, with an average number of steps approximately 4 steps fewer than the baselines. The performance difference between L-LLM and S-LLM with KD stems from their distinct approaches. L-LLM employs a global perspective to design each function with rules, but is susceptible to the influence of the current state, neglecting global planning. Conversely, S-LLM with LD initially abstracts the restricted area as a coordinate filtering function, which handles the output of filter valid moves, producing a list that excludes the coordinates of the restricted area. This function is then utilized by select best move to generate a suitable coordinate. Figures 6 and 7 illustrate the comprehensive planning and decision-making processes of L-LLM and S-LLM with LD, further validating the effectiveness of converting logic into functions. The significance of LD lies in its ability to enable S-LLM to retain more general capabilities, as it only uses a few function usage examples to fine-tune S-LLM. The authors propose logic distillation as a method to improve the performance of S-LLMs, which instantiates the logic of L-LLMs by converting human-provided rules into functions, establishing a function base. Through fine-tuning, S-LLMs will comprehend the usage of each function, enabling them to plan and make decisions function by function. This approach addresses the limitations of L-LLMs, which are difficult to deploy on most devices due to their large parameter scale, and S-LLMs, which fall short in performance compared to their larger counterparts. The research paper presents a comprehensive framework for analyzing complex systems, focusing on the integration of machine learning and dynamical systems. This approach enables the identification of nonlinear patterns and the prediction of emergent behaviors in high-dimensional datasets. The authors propose a novel algorithm, dubbed DYML, which leverages the strengths of both machine learning and dynamical systems to model and analyze complex systems. DYML combines a Gaussian process prior with a nonlinear dynamical system, allowing for the inference of underlying dynamics from observational data. The paper demonstrates the efficacy of DYML through a series of experiments on synthetic and real-world datasets, showcasing its ability to accurately predict chaotic and nonlinear behaviors. The results highlight the importance of incorporating domain knowledge and physical constraints into machine learning models, particularly in systems where data is limited or noisy. The authors also provide a thorough analysis of the algorithm's limitations, including the assumption of Gaussianity and the potential for overfitting. Furthermore, they discuss potential avenues for future work, such as the extension of DYML to non-Gaussian processes and the development of more efficient computational methods. Throughout the paper, the authors emphasize the importance of interdisciplinary approaches to complex systems analysis, highlighting the need for continued collaboration between machine learning researchers and domain experts. By integrating machine learning and dynamical systems, DYML offers a powerful tool for understanding and predicting the behavior of complex systems, with far-reaching implications for fields such as physics, biology, and engineering. In recent years, large language models have garnered significant attention for their potential applications in various fields. These models are trained on vast amounts of data and can be fine-tuned for specific domains to achieve remarkable results. In healthcare, large language models have been used to improve patient care by analyzing medical records and providing insights that could aid in diagnosis and treatment. For instance, a study published in the Journal of Clinical Oncology found that a large language model was able to predict patient survival rates with high accuracy when given access to electronic health records. In finance, large language models have been applied to tasks such as sentiment analysis and fraud detection. A study by researchers at the University of California, Berkeley, demonstrated that a large language model could accurately predict stock market trends based on news articles and social media posts. In dialogue systems, large language models have shown promise in generating more natural and coherent responses. For example, the Llama model developed by Meta AI has been fine-tuned for conversational dialogue and has demonstrated impressive performance in generating human-like responses. Bloomberg GPT, another large language model, has been specifically designed for financial news and data. It has been shown to be highly effective in summarizing complex financial reports and providing insights from large datasets. While these advancements are promising, there are still challenges to be addressed. One major concern is the issue of bias in large language models. Since these models are trained on vast amounts of data, they can perpetuate existing biases present in the training data. This could lead to unfair outcomes if not addressed properly. Another challenge is the need for high-quality, domain-specific training data. Fine-tuning large language models requires large datasets that are relevant to the target domain. However, collecting and annotating such datasets can be time-consuming and expensive. Despite these challenges, the potential benefits of large language models are undeniable. As researchers continue to refine these models and address their limitations, we can expect to see even more innovative applications across various fields.